In this video, we're going to look at chirality as it applies to molecules, and that will really start our discussion of stereochemistry, which is the study of molecules and how they differ in their three-dimensional arrangement. Okay, so what I want to do is, before we get into the notes, is let's look at just a model kit, like a plastic, toy arrangement of atoms. So what I have here is in the center, I've got a black atom, which is carbon. Then I've got colored atoms surrounding the carbon. There are 4 of them, and they are different. If you recall from our last lecture, I said that a molecule was chiral, overall chiral, not superimposable on its mirror image, if it had one carbon atom that had 4 different things attached to it. So that's what I'm trying to build for us now. I have a carbon. It has a tetrahedral geometry, which is what we're used to, and it has 4 atoms attached to it. So 1, 2, 3, 4 that are all different from each other. Okay, so if I consider now its mirror image, so let's imagine that we have like this mirror plane right here, and it's as if the molecule is looking into the mirror. This is what it would see. Okay, so I have the mirror image structure of that molecule. Now let's test to see if it's superimposable by trying to put it through. Okay, when we put an atom through, I like to try to align the carbon atoms. So, again, this is sort of a thought experiment, right? So I can't actually merge these 2 plastic models together. But if I could, you could see that I've got really good alignment of the central black atom, the carbon atom, along with the white atom and the gray atom. However, the red and the blue atoms do not overlap with each other. So we would say this is non-superimposable. Okay, so again, just to back up, we've got 2 structures. They happen to be mirror images of each other. Each one is the mirror image of the opposite one, and they are not superimposable. A property of an object that is not superimposable on its mirror image is that that object is said to be chiral. Now, let's actually break some bonds. So I'm just pulling off some things and rearranging them. So what I've done now is on the structure on the right, I've flipped the red and the gray around. Now you notice that these structures are no longer mirror images of each other, but if we look at this, they are now superimposable on each other. If I go like this, I've got alignment, and if you imagine actually merging these 2 models together, we would have great alignment of the central black atom along with the gray, blue, red, and then finally the white atom. Okay, so now we're superimposable, but we're no longer mirror images. Again, the molecule is chiral. The only thing it's superimposable on is, the mirror image of itself is not superimposable on the original molecule. If I go ahead and replace one of the groups with a white element, so I've got 2 of these, just the hydrogen elements that I had lying around, and let's take the gray one off in both cases. Now, in this case, I no longer have 4 different things attached. I've only got 3 different things attached. 2 of the things are white elements, so it's, all of a sudden we no longer have 4. So what's so magical about 4? Well, when you're less than 4, as you can see, we are superimposable in this current arrangement of these structures. So these structures are superimposable on each other. Additionally, there is a way to orient these structures so that they are mirror images, or more clearly seen as mirror images. So both of these molecules are mirror images. Both of them are, each can be superimposed onto the other. So we would say these molecules are not, this molecule shown here as its 2 mirror images is not chiral. So we need 4 different things attached to get to chirality at a central carbon atom. And that's important as we look to chirality in bigger molecules, things that are more impressive than just having a single carbon atom with 4 different things attached to it. Okay, so here we are. We're back at our notes. Let's remind ourselves that a molecule with a tetrahedral element with 4 unique bond connections is chiral. That is, it's not superimposable on its mirror image. So we looked at this in a model, but let's go ahead and draw. You know, what if I have some carbon with a 1, 2, 3, 4 thing attached to it? I then consider a mirror image of that molecule. So those two now are mirror images of each other. This dashed line is a mirror plane. It's as if one is looking into the mirror and seeing the opposite structure. Now there's no way, as best that I want to rotate this, for those two molecules to be superimposable. So I'm going to do a 180-degree horizontal rotation. So that's going to put one still at the top. I'm basically spinning this around 180 degrees, a half circle turn. And the reason why I want to do that is so that the 2 and the 1 line up with each other. Now when I do that, the 3 that was out front in the original structure is going to be in back. So I'm going to have to depict 3 as a wedge and then 4 as a dash. It was in the back, but as we spin a half circle, the 4 is now going to be in the front. Now what I want you to see is that if I tried to merge these on top of each other, I would say they're not superimposable on each other, because as I merge the molecules through each other, the 3 and the 4 do not line up. And I could rotate the molecule around if I wanted to get the 3 and the 4 to line up, but then the 1 and the 2 would not line up. Okay, so it's a trade-off as to what you're going to gain or lose, but the idea is that as it stands, the molecule can never be superimposed onto its mirror image. We would have to take that mirror image, break some bonds, make some bonds, but then we're no longer at the mirror image. We've changed the molecule entirely. So the point here is that the mirror image and the original structure are different from each other. And if they're different, the molecules are chiral. Okay, so chirality is a property of a molecule. And it really can be due to a single element within the molecule. We've really been focused on one carbon atom and showing what happens when it's attached to 4 different things. But it's a property of a molecule. A chiral carbon / stereo center. This is a property of an atom. So a single C atom with 4 different attachments. I'm going to scroll up in my notes and just revisit the original definition of chirality that I started with. So I'm just scrolling up. So I started with saying that a molecule with a tetrahedral element with 4 unique connections is chiral. Okay. The tetrahedral element with 4 unique connections is almost always carbon. And if you think about it, there are several elements that can attach 4 things and can adopt a tetrahedral geometry and can be then render the entire molecule chiral. But by and large, the vast majority of our chiral molecules, again, chirality is a property of an entire molecule, are chiral because they have elements of carbon in them with 4 different things attached to them. Just because carbon is so abundant in the universe, particularly in molecules, its ability to covalently bond to itself, as well as almost anything else in the periodic table, makes it really, and the fact that it needs 4 connections to achieve its valence, just makes it the grand, champion of chirality, I guess. But again, the carbon is not chiral. The carbon is considered maybe a chiral carbon, or it is a stereo center, as it's kind of centering in and starting our study of stereochemistry, which is the study of chirality. But we wouldn't say that carbon is chiral. That's not super precise. Sometimes it slips out. But the molecule is chiral as a result of that carbon atom. Again, the molecule is not superimposable on its mirror image. Okay, let's look at an example. So is it chiral? So what we're going to do is we're going to label, I'm going to draw a few molecules, and I want you to label each of these as being chiral or achiral. Remember, achiral is the term that we use to describe things that are just not chiral. So is it chiral? So again, I want to draw molecules. So we have this first example, and we would say that this molecule is chiral. I'm going to put up here, chiral or achiral. So is it chiral? It is indeed chiral. Why? Because we have to put a star next to, if we wanted to put a star next to a stereocenter, it would be at this carbon. Zooming in on that carbon, we would see that we have a CH3 this way, an ethyl group this way, which is a 2-carbon chain. Then pointing down is a wedge to a bromine. And for every wedge, there must be a dash. So I'm going to label the dash to the hydrogen atom. Okay, so we would maybe say the ethyl is 1, 2. Well, I'm going to be consistent with some notes you'll take for the next module. I'm going to start at the bromine, label the bromine as 1, the ethyl group as 2, the methyl group as 3, and the hydrogen as 4. Note that it's not the actual element that it's attached to, it is the group that it's attached to. In 2 cases, we've got, in groups 2 and 3, we've got 2 carbon attachments, but the carbon attachments are different. One is a carbon attachment to CH3. That's in contrast to a carbon attachment, which is CH2CH3, and that's our ethyl group. So we have bromine and hydrogen, which are completely different elements, but then 2 of the groups that are attached to our stereocenter, our chiral carbon, those 2 groups are attached by carbon atoms, other carbon atoms. Those other carbon atoms aren't chiral, but they do introduce new groups, different groups. One is only attached to 3 hydrogens. One has another carbon and vastly more hydrogens. So they're different groups, even though they're the same element. That's a key aspect of chirality. You can have different groups to get you to 4 different things, even if the elemental attachments are the same. Now, a bromine's a bromine, a hydrogen's a hydrogen, a methyl group is a methyl group. If I replaced one CH3 with another, if I replaced the ethyl group with another CH3, if I went down this road, this is now achiral, and the reason why is because the 2 CH3 groups are the same. Now, in another example, I'm going to redraw the same molecule that we drew to start, but I'm going to leave out the bromine wedge. I'm going to show the bromine as just a single bond. Is this chiral or achiral? Turns out it's still chiral. It's all about how many different things are attached. So, you draw a straight line to hydrogen. I don't know what's a wedge and a dash, so I'm just going to leave them as straight lines. The wedges and the dashes need to be defined at some point, but if they're not defined, if I don't give them to you, you just assume, well, they could be either wedge or a dash at bromine. So let's go ahead and just kind of leave them alone. So we have ethyl and CH3. We would put the star here. The star is equal to our stereocenter or chiral carbon, and the molecule is chiral. So I'm going to go through and I'm just going to highlight chiral and then put a star next to the stereocenter. Notice I wouldn't have a star in a molecule that's achiral because it shouldn't have a stereocenter. Let's keep on this first example, and we're going to look at a flipped version of this original molecule. So let's say that we have ethyl attached to CH3, but now the bromine is drawn as a dash, and then you would come in and say, well, for every dash, there's a wedge. For every wedge, there's a dash. If it's not drawn, then it must be an implicit hydrogen, something we don't have to draw for bond line structures. But if I go ahead and sketch it in, it's going to make solving this question a lot easier. Well, this again is still chiral. We've just flipped the wedge and the dash. And in fact, in this particular example where we flipped all of the stereocenters from wedges to dashes, that is going to be the mirror image stereoisomer, excuse me, the mirror image structure of that first example that we provided. And we're going to look at that a lot more in upcoming lectures, but I want to plant the seed now. So we have mirror image of number 1. So once again, we're chiral. We actually have the same stereocenter. Okay, so let's start to look at some more complicated examples. I mean, not, you know, we're just going to look at some more examples. I don't know how complicated they are. I'm going to go ahead and write them in. I'll let you get ahead if you want to. Okay, so a bunch of examples. I'm going to zoom out here. So in this first one, this is an example where we have wedges and dashes, but we actually don't have 4 different things attached. We often do this wedge and dash to try to remind people that we have tetrahedral geometries at our sp3 hybridized carbon atoms. But you couldn't go ahead and write a star there because there are 2 CH3s attached to the molecule, and the other groups are actually the same as well. So this first molecule is achiral. Now, if you notice, for the rest of the examples, I don't have any wedges and dashes, but that's okay. We don't need to, I mean, defining wedges and dashes clarifies a lot of things, but it's not needed to define that something is chiral or achiral in the vast majority of cases. Okay, so this next one is in fact chiral. We have a group here, which is like a, I'm going to circle this in red. This entire group is a propyl chain, which is different from this ethyl chain, which is different from this methyl chain. And I always like to remind myself, once I identify that stereocenter with a star, that the implicit hydrogen provides with a 4th group. So we're at 3. And I'm going to make sure this looks like an H. I'm going to draw an old school 4. Okay. So we have 4 different groups attached. This is indeed a chiral molecule. This next example, the only thing that really looks like it stands a chance is this group, but it's got 2 methyl groups. Methyl groups are the same as each other, so I would call that as an achiral molecule. Now, what about elsewhere in the chain? We've got H's everywhere is the problem. So there's no other group that has 4 different things attached to it, because CH2s and CH3s, they have multiple hydrogen atoms, multiple of the same element, hydrogen. So we can't add anything else to hydrogen, so it's kind of done. If it has a CH2 or a CH3, it cannot be chiral, or it cannot introduce chirality by being a stereocenter or a chiral carbon. So this molecule is achiral. This next molecule looks interesting, but it's recognized that the ethyl group here is the same as the ethyl group here. That's going to render the molecule as achiral. So even if I wanted to put a star there, it wouldn't work. Now, similarly, down here at this molecule, we don't have a stereocenter at the position I've starred because we've got CH3s, so the same group. However, if we go to this carbon, we've got a CH3. This is an ethyl group, and this is actually an isopropyl group. If you remember this from the 1,3 diaxial interactions, you don't have to. You just have to recognize that by having that additional CH3 at the end of the chain, we actually have a different group. So we have now 1 groups, 2 groups, 3 groups, and hydrogen makes 4 groups. 4 different things attached. That's going to give us a chiral molecule. Okay, now down here, if you notice, we've got a lot of stuff going on here, but what I have to emphasize with this question is a few things. Number one, chirality or chiral carbons slash stereocenters must be sp2, must be sp3, not sp2 or sp. So if we look at this carbon, it's got a CH3, it's got a carbon that goes off to a ring, a different carbon that goes off to the rest of the ring. It's potential that this molecule has is chiral, or excuse me, introduces chirality, is a stereocenter, because all of the groups that are attached to that carbon are different. I'll say it again. That carbon that I've just starred and put an X through, all of the groups attached to it are different. But it doesn't have 4 different things. It only has 3. It has the carbon going south, the carbon going northwest, and the carbon going northeast. But that's only 3 things. And just to emphasize, this is a flat carbon. It's not tetrahedral. So it must be sp3 and tetrahedral. Otherwise, you don't get this opportunity to be different than your mirror image. You don't have this opportunity to be non-superimposable on the mirror image. Okay, so it turns out that nothing about this molecule makes it chiral because it doesn't have any tetrahedral carbons with 4 different things attached to them. That's what you need. I mean, fundamentally, let me emphasize this. To be chiral, it's that you're not superimposable on your mirror image. That's the most important definition of chirality. There's a shortcut that works a lot of the time where if a molecule has a carbon that's tetrahedral with 4 different things attached to it, it then renders the entire molecule chiral. But again, the best definition is not superimposable in its mirror image. Let me just say something quickly about benzene, because it can trip us up. It's a little bit early in the game to explain the fundamental rules for why what I'm about to say is true, but it's a big part of organic too, and it's a really interesting part of chemistry in general. But if we look at benzene, so benzene is a 6-membered ring with alternating double bonds and single bonds. What I want you to do for the rest of the semester is not worry about whether I start my first double bond here or whether I start it at this position. So going forward, it does not matter. These 2 structures we actually show with a double-headed arrow, not an equilibrium arrow, and we put brackets around them, and we identify that they're actually the same. I'm not going to write this down. I'll write down what we need to know right now, but I'm just going to say it. Those 2 structures depict the exact same molecule. That's a phenomenon called resonance or resonance structures. Those 2 structural depictions are not isomers. They are the same molecule. What has happened here is we've taken something so complicated as a molecule that exists in a 3-dimensional universe, and we've tried to draw it on a piece of paper. Bond line structures work really well. We saw the power of that with chair structures. Chair structures describe something with actually, I mean, it's hard to learn at first, but a decent amount of simplicity on a 2-dimensional piece of paper. But come on, there's going to be some shortcomings as we try to depict molecules, these really complicated arrangements of atoms on a 2-dimensional piece of paper. Okay, so one issue is that sometimes we have to depict a molecule as multiple structures, and that's the case of benzene. It turns out that every bond between the carbon atoms in benzene is halfway between a single bond and a double bond. But that's really hard to depict, so we just show one of possible 2 bond line structures, and we say it's like an average of both of them, and it's a 50-50 average in this case. Okay, so these 2 structures are the same. So what does that mean for you in the context of chirality? That means that if and I guess you want to be careful about the double bonds just so you can pick up on this example. If I'm looking at this molecule, okay, you might say to yourself, well, the double bonds in each of those benzene rings are arranged differently. Does that mean that those groups are different from each other? And while the double bond depiction is different, the groups are the same, and the molecule is then not chiral or achiral. So despite differences in the double bond arrangement. And we will very rigorously look at this in detail in organic chemistry too. And it's really interesting. And yeah, anyway, I greatly enjoy it. But overall, this molecule is a chiral. So let's switch it up though and look at an example where we would want to pay attention to this. So if I took those exact same, let's be exact same rings, and what I did was, instead of keeping the rings just like this, I just throw on a methyl group, a CH3, at the end of one of the rings. Now this group and this group are different, and we have a group here and a group here. All of these groups are different. 4 different groups are attached to the exact same single carbon atom. That means that that is a stereocenter. And if we have a stereocenter present in a molecule, most of the time we have a chiral molecule. Okay, so we started diving into chirality at the molecular level. Looking at a bond line structure and identifying whether or not it's chiral is a critical skill that we'll need to kind of master stereochemistry. And stereochemistry will actually split this module, and then the beginning of next module. We'll kind of get to a certain level of depth I think is appropriate, and then continue onwards into module 4 with even more depth looking at stereochemistry.